So thank you for coming. Is this on? Yes, okay. I guess this is going to be a kind of a different seminar of what you're expecting, I guess. When I was thinking on what I was going to say, I was trying to prepare this presentation. Why do we care? Yes, I can tell you why do we care about the western boundary currents in the South Atlantic. But then I thought, as this is going to be my last seminar, I rather decide to tell you why did I care? Why do I care? How it happens that I end up having almost half of my career looking at that problem. So I remember when was it? I'm glad that Rick is here because he's the one that's going to understand this. Maybe he was there. Maybe he was there. Okay. For starters, doesn't matter. I don't know if you were there. Le Monde de 30 Years Laboratory, I think Columbia University, I think it was 1983 or around that, because I was making a presentation at the Friday colloquium, the one that was for the whole lab. And the paper was published in 83, so it must be around that. So a much, much younger version of me and terrified version of me, the only woman in the division, physical oceanography. I was making a presentation on a work I was doing in the tropical Atlantic. At that time, I was working in the tropical Atlantic. So here I am explaining, how I solved the equations. What did we find with a just simple two-layer model? How the reversal of the North Equatorial countercurrent is due to the reversal of the curl of the wind stress, and I talk about that. And when it's over, Taro Takahashi, you know who he is. Chemistries know who Taro Takahashi is. It was a pope over there. To me at that time, a very old man. He might be 20 years younger than me now, but he asked me, this is all very good, but where is all these waters coming from? What is the origin of all that circulation, etc.? I don't know what I told him. I told him something like from the South Equatorial current, whatever, and he let me go. But the reality is that I didn't know exactly where anything was coming from. So I locked myself in the library, terrified to go to the cafeteria and find Taro asking me where the water was coming from, and start looking what was known up to that moment about the origins of the waters that was composing all this circulation in the tropical Atlantic. And what I find out that I didn't know much, but it was not much known. It was obviously, these were the classic pictures, mostly done by, okay, I'm going, no. How can I go back to what I was? Yeah, this is the point. What it was known is that the western boundary, the Gulf Stream, was a strong one and counter a weaker Labrador Sea. Same thing for Kuroshio and Oyashio. And the very few observations that existed from spurs cruises that were done in the area, they were talking about a very weak Brazil current and a very strong Benguela current compared to their peers in the other oceans. So if the circulation is explained by the Sverdrup theory or the closure, all the boundary currents should have the same intensity. Of course, the Sverdrup closure doesn't include western boundary currents. But so Stommel suggested that the cause of the difference between the Brazil current and the Gulf Stream was found in the thermohaline circulation. This is all oceanography minus 101, but that's how it started with me, So what he was pointing out that the thermohaline circulation will have the Gulf Stream, what it will decrease the Brazil current in the South Atlantic. And Kirk-Bryan also was doing through modeling. He was talking about that due that the South Atlantic is the only one transporting equator-wide meridional heat flux. This is why the MOC was the reason why the currents did not follow the typical and classical pattern. Now, all these were results based on models. There were no direct observations made except for fewer cruises that were going on in the area, the big expeditions that they will take to Antarctica or to the South Atlantic. So I had this idea, which again, I was innocent. I thought it could do it, but I thought that, and I was looking at the very first general circulation model. I don't know if you ever heard about it. Semner and Chervin was like the first one. And I said, well, if we can simultaneously look at these three regions, we should be able to not only observe the boundary currents, but also determine what is the water, the result, why we end up over here, and maybe I can answer that. But of course, it took me years to get each one of them funded, and they all went in different time periods. Like here in the Brazil Malvinas Confluence, I started in 84, 86, and I finished in the 90s. For the Benguela region, we had two projects going in 92, 94, and then 97, 99. And finally, I was already here when we got funded the North Brazil Current Rings experiment. So it was not done at the same time at all, but more or less we have data at that time in those regions. So for the western boundary, we started a partnership that was a pilot experiment in 84 and 86 with the Argentinians. That continued with the biggest program that was Argentina and the United States and France. Alberto Piola and Christine Provost were my co-PIs in Confluence. And I worked with Alberto and Raul and others in the pilot experiment. And with this first partnership, we were able to complete the first time series, the surface and subsurface observations in the Confluence front. And we were at that time looking at the Confluence front mostly from the point of view of the understanding the South Atlantic gyre circulation and to be able to give values to constrain the models. And to even possible, we start talking about MOC. But at that time, we were still calling thermohaline circulation. And of course, they were important for fisheries and other stuff. So the initial observations were done with the very, very, very original inverted echo sounders. That's Gary, you might recognize. Okay. That's ones that produced the first ISS. Those series were like 18, like we have IS number 18. And we were using a very simple relation between dynamic height and travel time. Chris is still laughing at me because we were using that, because then he went to URI to get his PhD and he developed a more sophisticated way of analyzing the data. That results are more or less the same. So we look at basically at the transports and the motions at the Brazil Malvinas confluence. And we have three instruments. That's all what we have. Three instruments deployed over here across the Brazil current. This is a map of the Brazil current from CTD stations. And we got a value for the Brazil current about 11 to 12 sphere drops. And a ridiculously low value for the return of the Malvinas. And I think that basically the main problem we had was that everything was geostrophy. We were just using a level of no motion. We know now the Malvinas confluence is a pretty barotropic current, and you had to measure from surface to bottom. So, well, but that's the number we were getting. when we did the Confluence program, already we used I don't know if they were more sophisticated, but they were bigger and more difficult to deploy, that's for sure, instruments to do the IES. And at that time, if you see, there is a frame around there. We tested, we put it in the water with the frame to be sure that there were no leaking. And if there were no leaking, we recover it and put it back in the water. A lot of work to keep these things going. And this is in the region where we did this Confluence program. We have 10 IESs over here and 3 current meters at the Brazil, at the Malvinas current, because as I said before, this is a very barotropic, and you need current meters in order to measure that. Those were French. The Christine was doing the current meters, and we were doing the IESs, and Alberto and all his colleagues were doing the CTD work. These are pictures of where the front was located. The French had with them some chemistry, and they were doing PCO2, CO2, and nutrients. And so this was more or less the program. And we have some interesting results for that time. When up to that moment, we knew that there was large and strong variability at the confluence, but was at the surface. All what we had was satellite data for sea surface temperature. We didn't know what was going underneath. We do know that there were all Arnold took CTD data, etc., but mostly the variability of the fronts was related. It was observed at the surface. With the 10 ISs that we have at the confluence front, we were also able to determine, I can't believe I always do this, I don't understand why. I don't understand why I go backwards. I said in the right direction here. Okay. This variability was also present in the deeper ocean. Now, through the CTD data we collected, we were always able to determine that sometimes what you see at the surface is not, the front at the surface is not coincident with the front at 1,000 meters. And the variability of the front was related mostly to the separation of the Brazil current from the coast. So the further penetration of the Malvinas current, which pushed the Brazil current to the interior, and then the variability occurred. And it occurs between more or less 38 to 34, 35. And we have also a small, tiny model, a simple model to determine the motion of the front and the placement of about 100 kilometers. So the variability of the sun was related to the seasonal cycle of the wind, something that the models already say. Ricardo Matano had models about that, had a model that shows that the variability of the surface front was related to the variability of the winds, but we also noticed that in addition to that seasonal variability, there was the latitude, the mark, and a large interannual variability that was related to pulses of the winds out of the confluence, mostly at the Drake Passage, even though there was no relation with the pulses in the Antarctic circumpolar column. And we observe rings all over the place. These are the time series of the IESs, and you can see we have a large variability. So one cruise that might have take place one after the other might give you either a very strong or a very low transport, depending on when you were there. And that's the advantage, is valid up to date. But we still keep going with the Malvinas retained 3.5 Pedro, but Christine in the south was able to get the 50, 60th verdurus of the current barotropic. And this is the front. And we observe rings inside and outside, and cyclonics and anticyclonic. And this is the situation when the Brazil Malvinas retroflex returns, there are rings that are originated at the confluence. And we did study of those rings. We made a lot of numbers out of these things. Now that was then. Now, years afterwards, with the paper that we did with Brick and Gustavo, which is still going on, Gustavo's work is still going on up to 1818, we see that the latitude of the confluence was drifting towards the south, and there is a lot of people here that is working on the expansion of the gyre, etc. This is from the web page. And this is the one that was published before. So this is more of a now. Now, how did I get into the Benguela current? 1985, Arnold Gordon published a paper in Science. And he talks about the thermohaline fluxes and the importance of determining those thermohaline fluxes in the South Atlantic, and the role that the Benguela current plays in bringing in water through the Indian Ocean to the Atlantic. And he said at the time that a special attention has been given as the heat flux across 30 South in the South Atlantic is directed towards the north. Here we are all talking about things that nowadays no one even mentioned because it's very well known, you know. And again, attribute to the thermohaline circulation. So I knew how to work with ISS. Arnold is a total expert in CTD, water masses, etc. And we joined forces with Dale Pillsbury from Oregon State University because he knew how to deploy current meter moorings. So with the 3 PIs, we got funded to do the program that was called BEST. Arnold, like always, programs that have names like this, BEST. So we did the Benguela Sources and Transport project between 92 and 94. What we had over there is 3 cruises, 3 hydrographic services, and we have ISs and current meters. I'm going to show you later in another one. And basically what we wanted to know, not only what is the transport, but what are the sources of the Benguela current. Finally, we should be able to answer TAR over there, but and how this varies with time. Also, we were talking about the Agulhas waters into the Atlantic and the retroflexion, and looking at rings, eddies. At that time, we call it eddies. We didn't use the politically correct word of rings, that when it detaches from the main current, it becomes a ring. At that time, we still call it eddies. And this picture became something that people use for a long time. And this is one of the line of moorings. You know, we have IS current meter, and the hydrographic services. And for the first time, we envisage something that we call the Agulhas Eddy Corridor. And this is what we thought at the time. That's where the eddies that shed from the Agulhas current were getting into the Atlantic. And what were the origins of this Benguela current that generates here? And we said that it has different components. There has some component that come from the South Atlantic current that was feeding the Benguela current from the west. We have some components coming along the coast that we thought they were tropical waters origin. We have filaments and a shelf current. And we have the Agola's retroflexion. We measure for the Benguela current a value of 13 Sverdrup that I had to say that stayed valid up to date, more or less. Very interesting enough, we find rings or eddies that were of Brazil origin. They came from the Brazil current. They were shed at the Brazil current, and where we observe it here. We even have a...
Silvia,
yes?
back to that picture. So a simple-minded look at that picture, I might say that most of the Benguela current is actually coming from the center of the subtropical gyre in the South Atlantic.
6 Sverdrup.
Yes, rather than to the Agulhas current or its rings.
No, I didn't say that. This is down coming to how many are from the rings.
Oh, okay. But
okay, no, but the 6 Sverdrups are coming from here.
This is recirculating.
It's the detachment from the South Atlantic current going over there. It's already mixed. Okay. So these are the rings. Arnold got all excited because he always had his theory, and he's right. But I mean, a couple of years ago, he was proved right that the Agola's rings will detach from the retroflexion, will cross all over the Atlantic, and will get into the Brazil current. And then we have ring shedding from the Brazil current, and will come back. We observe it. But Matano's model, he has a model now that he's launching dye in the ocean, and he can see it, that it's happening. So I don't know, that rate indicate. Okay, so we have Agola's eddies or rings, and we observe Agola's, and we have Brazil rings. We find 7 anticyclonic eddies during the survey, and 2 were of Brazil origin. Now, we observed it with inverted ecocenter, and we said that we observed like 6 more or less rings, eddies from the Agola origin entering the Cap Basin. And that we said here, I think I don't remember the numbers, indicate that the mean available heat and salon per eddy, okay, were about 3. These are the numbers that we got at that time. I don't remember how many Sverdrups it's here. 0.077 petawatts were entering from the rings in the Agolas, and 2.6 Sverdrups. So it was just part of it that is coming from the Agola's retroflexion. The other is recirculated from the Atlantic. And there is an important component also coming from the tropics. So after we did that, and Claudia can relate to that. I think you were a student at that time in Germany. Johann Lucherharms, Olaf Bobel, and Tom Rosby were putting together an experiment that was called Capex. That was to study the circulation in the Cape Basin. And this time Phil Richardson came to me and he said, you know something about the region. I know something about Raffles floats, and I want to play with these guys. Should we write the proposal and do something together? And we did. It took us 4 submissions to get it funded, but we got it funded. And what we did was, we did surveys, CTD surveys, and we deployed Raffles and Alphos floats. These two sound sources were ours from Woods Hole. Those 2 were to Woods Hole. And so we launch Raffles floats over here with survey rings, etc. And we look at the entrance of the Benguela current and the extension along this side, what is the transport of the extension getting into the Atlantic. So we deploy the floats roughly around 30 south in what we thought it was the intermediate water, and we almost failed completely, but we got it at the limit of the intermediate water. So more or less they behave. And we have 3 crews over there. This is a picture on the satellite picture, and we surveyed rings, and we get the transport in perawatts per ring and in volume. And we have the trajectory of one of those rings. And it was a very intensive study for the Agulhas rings. Claudia afterwards continued observing some of these rings, correct? Further north in the Atlantic. So we have a good idea. And I don't know. This I'm going to tell you a story because it's more fun. I mean, this was a very fun cruise, and after we worked like for 20 days in the region, 21 days we were working, and we were facing a long transect to Recife. So when we left the region, we were passing by Santa Helena, the island where Napoleon was in exile. And so, please, 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 let's try to stop. And so went to the captain, please, please, please. And the captain and I, we went to the State Department, and they allowed us to stop in Santa Helena. It was fantastic. The ship couldn't get there because there was no port. So we had to go in Zodiacs. And the whole population of the island was sitting there waiting for us. So we spent a day there, and it was fantastic. But the interesting part that this was during the apartheid. So there was almost no traffic to South Africa. So these people got provisions once a month. When we left the island, there was no one single drop of beer available. They drank all the beer of the island. Okay, US vessels are dry. I'm glad of that. They drank all the beer. But it was fun. Those were good times. Interesting enough, we deployed the draft rifles at 30 south, thinking they were going to go north. Here they go. They go south. Okay. Luckily, only for 3-4 months, and then turn around. So we were able to get the trajectories of the rings, but I'm talking about 19-something. The experiment finished when we just were crossing the mid-Atlantic ridge. So we never knew the end of the story. But still, we were able to determine the boundaries of the Benguela Current, the part that's going into the ocean. We measured that was around 15 sverdrups, and 1.5 sverdrups are transported by 3 Agulhas rings. That was Bali Sounds. In that time, we said, at that moment, rings that cross the mid-Atlantic ridge each year. This is what I was doing, and this is kind of a me talk, but far more work was doing in the area. In the western boundary, the Argentinians and the Brazilians had a lot of work doing. Alberto and Edmond, they have a huge program still going on that is called SAC, and they're looking at the whole area and the country. So they have plenty of publications over there. And Christine, the French woman, with Martin Saraceno, they have a race here for Malvinas. But there still were questions about the origins of the deep western boundary currents, and I gave a seminar about 2 years ago about that, and there is a publication, so I'm not going to talk about that. But there was a question that the Germans have, looking at model and observations, say, well, the North Atlantic deep water, the deep western boundary current coming from the North Atlantic, when they reach the mid-Atlantic ridge, breaks into rings, and there is no more water, North Atlantic water going deep south along the coast. They all move crossing the Atlantic. But with that paper that half of you were co-authors, we look at all the data and models, and we know that the deep western boundary current around here is composed by North Atlantic water, so it's part of the MOC. And on the Eastern Basin, they also have a lot of work. Johan Luchofars, he got this award that is one of the most important in South Africa. He died right after that, poor guy. But he has written books on the Agulhas currents, and there is a lot of work. And Arnie make a big noise when he ran these models, saying that there was these Agulhas rings invading the Atlantic, and everyone started looking at that. Sankey just sent us a paper. Where is Sankey? And this is, I think that our colleagues from CEMA published this with other people, showing the importance. Lisa Dill on the other side. This is from Science too. So what I told you was mostly what I did, but there's tons of things done by other people far more important, not counting all the satellite observations, and I just put some names that came to my mind that were in that order, because Bill Haxby was the first one just following from GOES. I don't remember what's the name of the first satellite, the rings on the Atlantic, and today there are plenty of work. Gustavo also did a lot of work in both sides, some of that with me. So finally, in 2007, we were able to get something coordinated in both sides, with all these people working in one side and the other. In one of the most beautiful places over there in Buenos Aires, we have a meeting, and we came together with CEMA, South Atlantic Meridional Overturning Circulation. And here we are already talking about not just thermohighland circulation, just to measure the strength and the variability of the meridional overturning circulation. We also want to know meridional heat and freshwater transports in the South Atlantic. And we think that is all important to determine the climate system. This is a picture you all here have seen many, many times. This is the original planning for CEMA. We have simultaneous measurements in both basins, and we have an XBT line that is going back and forth from Cape Town to Buenos Aires, more or less 4 times a year. And then we have the Good Hope lines going down to South Africa, the Drake Passage, and there's our Samba line around 34. You know about this. This is what is going on over there. So, as we said before, one of the things that we want to do is they will allow us to calculate the meridional heat transport, but in order to do that, we need to obtain measurements along the line from coast to coast and from surface to bottom. These are the measurements that we have in both sides. Chris is going to give a talking today. And I'm going to give you an example. This I showed it before, but I mean, why do we need that? Look at this. This is what we knew before we had got the first measurement with Molly here. This is what it was known from numerical models, direct observations, inverse models, and air-sea fluxes of the meridional heat flux in the South Atlantic. Minus 0.23 to 1.05. Numbers were all over the place. And it's normal. There was no data. That was all, I don't know, pure imagination. I don't know. Okay? Look at this, the distribution of data. Look at today. No data, no satellite, no data. That's why the numbers were all over the place. With Molly in 2007, we got the first one here from XBTs. We have MOC and meridional heat transport. We have it from altimeter for 810. This is now is the Gulf ship line, and from Argo floats. Argo and altimeter are very similar because with different methodology, they are more or less using the same data sets. It's the Capex Poseidon and interpolated with Argo or vice versa. With the XBTs, we needed, the XBT gets to 800 meters, so we had to make assumption for the depth. We didn't know what's going on in the deep. So all of these measurements, even though they're very variable, they need to combine all the data sets. None of them can do it by itself. So we need to get together and do it with all the observational systems. I thought we were going to do it. I don't know what happened. We didn't finish it. So what is CEMA providing to prove this estimate? The boundary current. This line, this here is the absolute Brazil current transport, Maria Paz. She's working and the paper is going to come very soon. This is the Brazil current, absolute transport. The mean is minus 13. If you remember, we got 11 that time. It's not so bad. But it has these big jumps, which I still have problems with it. I mean, in the sense that when we have a positive, what I assume is that we are not measuring, that we don't have to count that, because if it's positive, it's to the north, means that the current moved from the instrument, so we are not seeing it. And this is the deep western boundary current. Chris is going to give a seminar in 2 days, so I'm not going to tell you much about it, but we can measure it. You can see that both components at the surface and at the depth, they have a large variability, so 10 series are needed. Our colleagues from the east boundary are still working on their paper. We don't have the results yet. So now we know why we care about the South Atlantic. We needed to close the budget. We needed at the boundaries, we needed to close the budget. So what do we know? What do we know up to now? We know, and no one disputes that anymore, I think. But well, this is, of course, is the only basin extending to high latitudes that has transport. But what it is important is that we need to do it not only in the North Atlantic, but also in the South Atlantic, because the South Atlantic is not a passive ocean. We have from models, this is a model, a study that we did with Matano's model, in which we show the transformation of water masses in the Atlantic, basically mostly in the Brazil-Malvinas confluence and in the Cape Basin. And also, you know, these are the Argentinian observations. Daniel Valles, I think he's writing his thesis or I don't know, something, but it shows in this section so the different water masses and the transformation. So it's not that you have water coming and going out, you measure here and measure there. No, there is a lot of transformation. And even though there is a lot of transformation, there is also the income from the Indian Ocean and from the Pacific. I love these floats. Sorry, I wanted to update it, but I didn't have the time. But you see, this is the Malvinas current, a branch of this circumpolar current. So being open to the Pacific and to the Atlantic, and there is the Atlantic circumpolar current. So all these properties are connected. And Arnold, for example, he thinks that the ACC is the real MOC, because that's the one that's mixing everything on the oceans. But we have not only the waters that are forming in these two regions, but some components coming from the boundaries. We know, and this is also work from here, that's why I picked this, that it's important to measure it in the South Atlantic. We have the work of Shanqi and the work that Husman did, relating, I think in the next one is even more clear, relating the meridian, the ocean heat transport at 34.5 south. That's where we have our instrument in relation with the global precipitation. And also, I forgot to put his name. This is Drieghout, Sebring. All the work that the guys from the Netherlands did, it was perfect for us because they determined that 35 south is the place where we had to measure the fluxes, because that's where we can get the salt transport, the freshwater balance, and the this measurement controls the stability of the MOC. And HMO just published also with half of us here a paper about that I think is coming now. It's very good. So what do we care? We know that in order to observe the fluxes, we need to be able to close the observing line from coast to coast. We know that we need precise observations of the western boundary. And we know that due to the large variability, their time series are needed. We are not there yet. We still would need to close the western boundary. I don't know how many proposals went in, and we didn't get, but we need mooring. We need a mooring. We need a carbon meter mooring on the shelf. Hopefully, we'll have it one day. So where are we now? The numerical models illustrate the importance of what we are doing, but it's going to be the case to be, well, maybe centers, but I hope decades, that when we will be able to actually determine the impact of our observations in the real world, not in the model. And that's it. That's it for me.